All right, welcome to another exciting episode here of Advanced Level Chemistry. Spain Park. Today is Monday, May the 5th. May the 5th. We have exactly 14 days of school left, okay? And only 10 of those, including today, are really going to be like learning, whatever, because the final week is going to be your exams. And you get to take this one on what, on Tuesday, right? All right, so we're getting ready, we're ramping in, we're closing in. We got 1 unit left, 4 pages of notes, okay? But we already know a lot of it. So we're gonna go fast. The biggest thing that we're gonna have to focus in on with acids and bases is how to calculate pH, what is this whole thing of pH, and just kind of go from there. But today we want to kind of look at the definitions of what an acid or what a base is. But we've already done some of these definitions. So what is an acid? How do we know if something is an acid?
It has hydrogen.
It has hydrogen. Where is the hydrogen?
Right.
At the beginning. So if I put an H onto any one of these anions, I'm going to have an acid. We've already learned how to name them. Okay, we've recognized them. We've talked about them in solutions in terms of electrolytes. Okay, so if I put in, the acetate one is weird, so I'm going to skip it. But if I go HBr, I know that that's bromide. Does anyone remember how to name the acid? Hydrobromic acid. Carbonate is CO3 minus 2. So how many hydrogens would I need on it to make it the acid? 2. So it's going to be, but carbonate is going to be called carbonic or carbonic acid. So then you go down to chlorate. HClO3 would be chloric acid. Go down to ClO2 minus is chlorite. HClO2 would be chlorous acid. So we already know how to recognize the acid. So that's nothing new. What ion is present? Whoops. Just tighten it down. Turn it. It'll tighten when you turn that. Okay. So what ion is present in bases? Hydroxide. The hydroxide ion. And remember, our strong bases are our block B: lithium, sodium, potassium, rubidium, cesium, strontium, and barium hydroxide. They're the ones that are very soluble. So we already know the bases, the basics, the fundamentals of acids and bases. But let's look at just some common things, okay? We can just fill this in about acids and bases. Let's just get rid of that, do this. First off, just some clarifications on this part. This is our salt crystal. Salt, NaCl, is what type of compound? Ionic or covalent? It's ionic, right? Metal and a non-metal. Again, ionic compounds are composed of ions. So when they dissolve as ions. So when it goes into water, we say it dissociates into ions. The ions are already formed. All that happens when you put it into water is the ions break apart from one another. They just dissociate from one another. So I'm actually going to skip down here. It says, so ionic salts completely dissociate. Okay? Completely dissociate into ions. The only way that they can dissolve is as ions. Okay? However, if something ionizes, the process of ionization, that's the formation of ions from a covalent molecular solute. So electrolytes, we're combining all these different things. There are solutions that conduct electricity because they contain what? Ions. Okay? So if a covalent molecular substance ionizes, we'll have some ions. If an ionic solid dissolves, it's going to dissolve as ions. Okay? But, okay, what are our 3 types of electrolytes? three solutes, three different types of solutes that are electrolytes. Salts, because they completely dissociate into ions. Acids and bases. So bases are really just a special type of ionic compound. But acids are covalent molecules that ionize. Okay, so this is really generally only acids that do this. But acids don't always ionize completely. Covalent molecules have varying degrees. And that's kind of what we're going to talk about. That's what pH kind of measures. Varying degrees of ionization, because most covalent substances don't ionize at all. Again, this is going to be only acids. Most covalent substances just dissolve as molecules, non-electrolytes. Sugar, alcohols, and all the things that we just talked about with non-electrolytes. So this is the definition that we already know. Does anybody remember, nobody in first period remembered this, but do we know the name of that ion? The H3O plus ion? No? I can't believe, I thought for sure that I've talked about this, it just didn't stick. Okay? This ion is known as the hydronium ion. Forms hydronium ions in water. That's H3O plus. It's the H plus just attached to a water. So if I look at this reaction right here, I'm just going to draw it out, and I don't know if you can draw this on the side or somewhere, but if I look at HCl, chlorine, oops, is like this, and then water is like this. So when I put the two of those together, I'm making H3O plus. So what does that mean? What's going to happen? How do I get H3O plus?
You disconnect the chlorine from the hydrogen and then add.
So the hydrogen gets added to this, right? So the bond gets broken, but the electron gets left behind. Now an electron's an electron's an electron, so there's no real difference between these electrons. I'm just putting an X just to kind of show where it came from. Okay? So hydrogen's electron is no different than a chlorine's electron. We've learned that. But this is going to be minus because now it has an extra electron, but the water is donating the pair of electrons, and I get my hydronium ion. Now in the Arrhenius definition, what makes an acid is the presence of this ion. It's not how much of this you put into the water that makes an acid an acid. It's how much of this does it make. This is what makes an acid is the presence of this ion in solution. So notice here, this is a strong acid, 100% ionized. This is a weak acid, but it's still going to produce this. What the difference between strong and weak, though, is what? 99%. So what does that mean about the amount of H3O plus here versus the amount of H3O plus here? If I put 100 molecules in here, and 100% of them go here, how many am I going to have here? What's 100% of 100? 100, thank you. I'm going to get 100 of those. I'll have 0 of this left at the end. All of them are breaking apart. But if only 1% of these ionize, if I put 100 of these in, how many of these am I going to get? 1. I'm going to have 99 left of these. So 99 out of 100 is all like here. Now they're both producing H3O plus. They're both classified as an acid. Which one's the stronger acid? The top one, because it has a whole lot more of this. You're putting in 100 of each one. You're putting in the same amount of each one, but what makes an acid strong or weak is how much of this does it actually produce. Okay? So it's this ion that makes an acid an acid. Anything that makes this ion is going to be classified as an acid. What ion makes a base? Not hydroxide, you read well. Okay, so the hydroxide ion, time for a new pen. Anything that produces the hydroxide ion, this ion, that's going to be a base. So again, our strong bases, lithium, sodium, potassium, vanadium, cesium, strontium, and barium, those are the ones that are basically, they're ionic compounds, but they have the hydroxide ion. When you put them into water, they dissociate into those ions, so they dissociate completely, so we get a whole bunch of OH minus ions. That's my Arrhenius definition. That's named after Svante. That's V. Svante August Arrhenius. And he was a Danish chemist. And he just kind of did a lot of the preliminary work, late 1800s, early 1900s, about how things break apart, how things ionize in water. So that's been our that's been our common definition that we've used all year long for an acid and a base. Well, I'm going to save that. All right. Now that's a nice definition there. So very narrow definition. All acids produce hydronium. All bases produce hydroxide. Let me just kind of move this up and get all the base stuff in there. Okay? Now the problem, the challenging thing about a weak base is that they don't have hydroxide in them. Now it's still making it, by the way, this is a double arrow. It didn't translate through when it went from Word to Google Docs. Again, it's making the hydroxide, but it's a weak base. It's only making a little bit. The problem with ammonia and weak bases is when you just look at this and you put it in water, it's hard to know that that's a base. Acids are the positive thing, whether it's strong or weak, the positive thing's hydrogen. We memorize the 6 strong acids. We know any other acid is a weak acid. But to recognize this as a weak base, that takes some chemistry knowledge. Okay? We're not going to get into very much of that, but I do want to kind of explain how that works. So here's ammonia. Let me draw it. Here's ammonia. Hydrogen, 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 lone pair. Plus a water. Okay? So now when we look at this, how do I get NH4 plus and OH minus? The hydrogen's going to go to there. Right? So now we're going to get the hydrogen, 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 but it leaves the electron behind. So again, it's just going to be an H plus. Now we're forming a covalent bond here. We're going way back when to chapter 6. Both electrons come from the same atom in the shared pair. It's called a coordinate covalent bond. but it's just like this bond once it forms, because an electron's an electron's an electron. So nitrogen's donating both of the electrons in the pair, but we're getting a bond, but because it left its electron behind, it's just the positive charge coming over here, so now it's NH4+. But this is still a covalent bond. And what's left? An OH. That hydrogen stayed there, but now we have another lone pair, just the positive left, leaving the negative electron, so now that's minus. So we have an NH4+ and an OH-, but because it made this hydroxide ion, it's a base. This is an acid because it produces hydronium. This is a base because it produces hydroxide. Anything that makes this ion in water is an acid. Anything that makes this ion in water is a base. Got that? All right. I love a good bacon and eggs breakfast. But when you think about how it gets made, the hen that doesn't have bird flu, the hen, we're having this egg crisis because all the birds are having to be killed because of the bird flu. But the hen can be very focused, committed to making the perfect egg. Lays those 2, 3 perfect eggs for that bacon and egg breakfast. Can be very proud of those eggs for the bacon and eggs. Committed. Oh, I did a good job. But the pig's going to look at that bacon and eggs breakfast from a different perspective. The pig's going to have to be a little more dedicated to that meal. It's going to cost the pig a little bit more than it costs the hen. Got to give everything. Completely dedicated. So you committed to being your best? Or are you completely dedicated? Are you giving it your all? Are you willing to sacrifice it all to be your very best in whatever you choose to do? It's a big difference. Different perspective. A little life lesson in there. Looking at this, we're going to look at it. Arrhenius looked at it like the hen, but now we're going to look at it from the pig's perspective. Completely different perspective on the exact same thing. Okay? Y'all are ready to go, right? Give me a test right now, Mr. Hobbs. I'm going to ace it. No. Got to finish the year strong. All right. That's the good, the difference between just being committed to something versus being completely dedicated. All right. Bronsted and Lowry were two different scientists. They did not work together. Much like Leibniz and Newton discovered calculus separately, but at the same time, Newton just was able to publish first, so he gets credit with it. But according to Mr. Carboni, most of the calculus that we do nowadays is more Leibniz-based calculus than it is Newtonian calculus. I don't know what the difference is. It's been way too long. But Bronsted and Lowry must have published about the same time because they both get credit for it. So it's two different guys, worked separately, came up with the same definition. They didn't care about what got made over here. They wanted to know what's going on over here on the left. Arrhenius was all about the product. Bronsted and Lowry all about what's going on with the reactants. So a Bronsted-Lowry acid is a molecular ion that is we call it a proton donor. So, what is a hydrogen atom composed of? What subatomic particles make up a hydrogen atom? A proton and an electron. But if we leave the electron behind and we're donating the H+, the hydrogen without an electron, what's really left? If you have a proton and an electron, and it leaves the electron behind, just the proton. So an H+ ion is really just a proton. So Arrhenius, Bronsted and Lowry all talk about proton donors, proton acceptors. That's just your H plus ion, because an H plus ion is simply a proton. Okay? So the base, in this case, and here, notice this is donating the proton to the water. The water is accepting the proton and becoming H3O plus. In the Arrhenius definition, water is nothing. But in the Bronsted-Lowry definition, water now becomes a proton acceptor here. So this is donating, so this is an acid. But in the Bronsted-Lowry, this is going to end up being a base, because it's a molecular ion that is a proton acceptor. So in this one, what's the ammonia doing in terms of the H plus? Donating or accepting? It's accepting, which makes it a base, but what's the water doing? Donating. So it's actually considered an acid in this reaction. So what we get here is that the Arrhenius definition is the most narrow. So here's my Arrhenius definition. Acids have to produce H3O plus, bases have to produce OH minus. Okay, that all take place in water. They're very constrictive. The Bronsted-Lowry definition just expands it some. But listen, very important point. I'm pausing for effect. The definitions never contradict each other. You're never going to have something that's a Bronsted-Lowry acid and then all of a sudden be an Arrhenius base. It's just going to expand the definition to include some things that wouldn't even be considered an Arrhenius anything. Water being the main example. In Arrhenius, water is just a medium that it's taking place in. It's neither an acid nor a base. But in the Bronsted-Lowry, okay, it's not only defining HCl as the acid, now it's defining the water as the base. It's expanding the definition. Okay? So it's just making it more broad. Never contradicting. So if I can look at this and say, oh, this made H3O plus, it's an acid. I know HCl is going to be an acid by, there's three definitions by all three definitions. They're never going to contradict one another. So if you know it's an acid by one, it's an acid by all three. They just have a different perspective on why they're calling it an acid. All right. We were just talking about Spanish and Portugal and all this stuff. So in Spanish, we have the verb star. And we have to conjugate the verb. Any of y'all take Spanish? Okay? Okay? Or no Spanish? Okay. So I take a star. Don't get on my pronunciation. So we go estoy. We go estás. Está. Estamos. Están. Go to Spain. Estáis. Okay? Gracias. Okay. Now, so they're all forms of the same verb, star. We just conjugated. We showed it in different kind of forms, but they're all related to one another, right? They're all parts of a star. Well, we have what we call the conjugate acids and the conjugate base. The conjugate, it's related to, it's just a different form of the same thing. So if I look at HCl right here, HCl is the acid, okay? Well, the Cl minus, once it donates a hydrogen, now that it lost one, now that it has room, it has the ability to accept one back. But these two things are related to one another. The only thing that's different is it's missing one hydrogen, but this obviously came from that. So we call this, because it's an acid, it donated, now it has the it has the ability to accept one back, or if we look at the reaction going right to left, it's a double arrow, it can go either way. Right to left, what is this doing to go from here back to here? It's accepting now, right? Which makes it the conjugate. I'll go ahead and write it out. The conjugate base. And what's the H3O plus doing to get back to water? It's donating. This to get to here is donating the hydrogen back to the chlorine. So we call this the conjugate acid. But these two things are related to one another. They're similar, just different forms of the same thing. These two things are related to one another. So we would call this a conjugate acid-base pair. And this is a conjugate acid-base pair. The two things that are related to one another. In any Bronsted-Lowry acid-base reaction, you're always going to have two conjugate acid-base pairs. An acid with its conjugate base, its base with its conjugate acid. So if I go down here, and I put another example, we already have that one up there. But if I put another example, let me just say HNO2, okay, plus water. Okay? This is the acid. So what acids do with hydrogens? HNO2. It's the Bronsted acid. So what do acids do with hydrogens?
They lose it. Or they transfer it.
They donate a proton, right?
Yeah.
It's right here. They donate a proton. So if this donates a proton to the water, what am I going to make?
H3O.
Okay, so I'm going to make H3O plus, and what was the other thing going to be? NO2, but I lost the plus, so it's going to be NO2 minus. Okay? So an acid is always going to make a conjugate base. Once it donates the hydrogen, it now has the ability to accept one back. And there really needs to be an arrow coming back here. The reactions can go both ways. So acids make conjugate bases, bases make conjugate acids. Now what did we say again was the difference in strength? How many of these they make, right? Okay? So this is a strong acid, which means that 100% of them break apart. What does that mean then about this bond between the hydrogen and the chlorine? If 100% of them break apart, it's weak. Okay, the reason is because this is very polar. It's pulling the electrons this way, making this very positive, this very negative. Okay, but 100%, this is very weak bond. It broke up easily. So what does that mean about this Cl minus's attraction to get a hydrogen back? If it got rid of it 100%, is it going to want to get one back? No. It's listening to a lot of Taylor Swift. We're never, ever, 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 I mean like never, getting back together again. Okay? I know I didn't sing it right because I don't listen, but it's never. We're just never getting back together again. Okay? There's a girl actually in my AP chemistry class that got to go.
Yeah.
Got to go. Wanted to see a Taylor Swift concert, but the only one that was still available or something was in like Scotland. So they flew to Scotland to go to a Taylor Swift concert.
That's a pig right there. That's dedication.
Yeah.
My sister didn't.
That is dedicated to being a true Swiftie.
I remember my sister didn't decide she wanted to go to a Taylor Swift concert until she was out of the country, like past all of the American ones. My mom was like, "Listen, if you wanted to go, you should have decided months ago."
That's right.
When she was still
I
there.
know.
We are not going.
But You know, I said, more power to you, dedicated. I just wish, you know, I wish I could go Scotland. So maybe I'll go to Portugal, who knows? All right, so here's the deal. If it's a strong acid, that means it readily donates, 100% donates the hydrogen, which means the bond between the hydrogen and the anion is very weak. So the anion that's formed, the conjugate base, is going to be a very weak conjugate base. It's not going to have much of an attraction for a hydrogen. A strong base has a strong attraction to get the hydrogen back. So if I look at this, though, this is a weak acid, which means it only donates a few, less than 1% generally of these hydrogens. So when it gets over here to NO2 minus, what do you think? Does it want to get the hydrogen back or not? If it only was willing to give up like 1 out of 100. Yeah, it's going to have a much stronger attraction to get that hydrogen back. So this is going to be the way it's normally going to want to be. So 99 out of 100 are going to be like this. Only 1 is going to be there. And so if another one goes over there, then it's going to come back. Majority of the molecules are going to dissolve like this, not like that. So the weaker the acid, the stronger the conjugate base is going to be. I got it. Okay? Just put it on my desk. So acids and bases, according to the Bronsted definition, are always opposite. An acid makes a conjugate base, a base makes a conjugate acid. The stronger the acid, the weaker the conjugate. The weaker the acid, the stronger the conjugate is going to be. So it's always opposite. Acids make conjugate bases, bases make conjugate acids. The weaker the acid, the stronger the conjugate. The stronger the acid, the weaker the conjugate. Opposites. Okay? Opposites. Those of you that just came in. Okay. So if I look at this one right here, this reaction, we said this is the base. So what's the conjugate of this one? Which one's related on the product side to this one? The NH4. Notice that this accepted a hydrogen. Now this one, if we're looking at it for going from right to left, how is this one getting back to this one? It's giving the hydrogen back away, correct? It's donating the hydrogen. So that makes this the conjugate acid. Remember, a base is going to make a conjugate acid. Notice that the water donated a hydrogen. It's an acid. So what is it doing to come back this way? In terms of hydrogens. It's accepting one, right? So this hydrogen is going back and making the water. So the acid made the conjugate base. So this is my other conjugate acid-base pair. I have two. This is a conjugate acid-base pair. That's a conjugate acid-base pair. And we're going to start the day with this worksheet. I'm 4 minutes ahead in this class than any other class. So we'll take 4 minutes to just look at the beginnings of this. Okay? So if I look at it here, let's just look at questions number 1 and 2. 1 and 2 right here. And you want to write these just at the bottom in your notes or whatever, but I want you to identify the acid, the base, the conjugate acid, and the conjugate base. Just in number 1 and number 2 only. You can either do it in your head, you can do it on paper. I recommend you do it on paper.
Where is that?
It's not. As I said, it's the worksheet we're going to do tomorrow, but since we're 4 minutes ahead, we'll start with on 1 and 2 ahead of time.
It's not. That's funny.
I've got no shot.
To be honest, I don't think I have a shot. I might.
Mr. Hobbs, unrelated question. On the exam, when are we getting that study guide for it?
Probably this week some point.
Okay. Do you have it like done or you print it
Well, I have
out?
to look and just see, make sure.
That's crazy.
What did he say?
Effective.
We're getting our exams
Okay.
like this.
Are you gonna post it digitally or are you gonna print it out for us?
We're that close.
I usually print them out just because I like
I guess that is a good
paper and I
thing.
don't like trees.
I'm getting my English.
Just, I'm just.
Is it gonna be do it all or like extra
Yeah, this is
credits?
gonna be a do it all, and there's points for it.
Okay. So you'll post it, the answers a couple days before, I'm guessing?
Well, you have to have turned it in, I will have to see it completed to get points before I
Yes.
post the answers, yes.
So you'll have us, you'll check it one day and you'll post the answers after?
Yeah, something like that, yes.
Okay.
Okay, do we have an answer for this? I'm gonna look at this. How is HCl changing to go from here to here? It's losing hydrogen. How's NH3 changing to go from here to here? Gaining. So in other words, and nitrogen always has a lone pair. When you do the Lewis dot structure on ammonia, on anything with nitrogen, it's got the 5 valence electrons. It needs to gain 3 more. So the lone pair, every nitrogen is going to have a lone pair. That's why it acts like a base. It can accept the H on that lone pair. Okay, that's kind of the higher level AP type stuff that we're going to learn, but I'm still throwing it out there for you just to kind of let it sink in over the summer. So the hydrogen gets donated, actually it'll be about a year from now because we do acids and bases at the very end in AP too. So that it's donating. So this is the acid. This obviously then is the base. So what does that make this? This is your conjugate acid. So this is a conjugate acid base pair. What does that make this?
Conjugate base.
Conjugate base. Okay? Now I look here. What's the OH minus doing in the reaction? The hydrogen is being donated to this lone pair on the, and it's actually got 3 lone pairs. So that makes this an acid or a base if it's accepting. This is the base. That makes this the acid. So what does that make this? The conjugate acid. And this is the conjugate base. So my 2 pair, this, the OH minus, which one on the product side is related to the OH minus? H2O. Which one's related to the HCN? The CN minus. So these 2 are pairs, and these 2 are pairs. When I say what are the conjugate acid base pairs? Okay? So the 2 main definitions. I'll just tell you, the Arrhenius definition is the one that we use the most because pH is everything is in water, and all the pH and all those things that we're going to do are going to be based on the Arrhenius definition. Bronsted-Lowry is a little bit broader. We're just going to touch on this 3rd one, the Lewis definition. It's not even, they don't even include it on the AP test. However, when you get to college, organic chemistry, which is your second sophomore year chemistry, it's all about Lewis acids and bases. They do everything following the electrons, and so we'll look at that. All right, so you guys have a great day, and we'll see you tomorrow, and go Jags.
I'm gonna watch that video.